Hello everyone, thank you for coming to today's Seismic Academy. Our session today will be on torsion, a critical topic in solid mechanics. So before we start, I would like to give a little background on myself. I'm going into my third year of civil engineering at the University of Toronto. I have been on Seismic in both my first and second year as a general member and construction lead respectively. This year I'm a junior structural design lead. I hope this session will help you further your understanding of the concept of torsion, which is important when considering how members behave along a tower, specifically when looking at torsion that's caused as a result of the weighted rods that are added to the tower. If torsion is not properly accounted for, the tower may experience failure in shear as a result of torsion. So today, these are the topics we'll be covering. So first we'll look at what is torsion, then we'll look at shear strain in cylinders, then shear stress in cylinders, how to find the twist angle in cylinders, which we will define later, and transmission shafts. And if you're wondering what transmission shafts are, they're essentially pulleys and gears, or what you use to transfer power across a system. So what is torsion? Torsion in our case is defined as a twisting moment on an element and is measured in Newton meters. This twisting moment is also referred to as torque. When examining torsion, we look at cylinders and consider the x-axis to be the axis normal to the cross-sectional area, which is the axis the torque acts upon. The torque sign convention follows the right-hand rule. You point your thumb in the direction normal to the cross-section and curl your fingers as shown in the figure on the bottom right. The direction of your fingers curl in is the positive torque direction. Positive torque may also be denoted by two arrows going normal from the cylinder's cross-section, as we will see later in some later figures. So before I proceed, does anyone have some quick questions about my definition of torsion? Okay, I'll proceed then. To further our understanding of torsion, we must look at shear strain. Shear strain is developed as a result of torsion in a cylinder or any other element shape. It is denoted by gamma and is expressed in radians. Shear strain is defined as the angle along the cylinder's length between a point on a cylinder pre-rotation and post-rotation. As you can see on the figure on the right, an example of this would be pairs B and B prime and C prime respectively. For a cylinder, this angle is the same for all points at an equal perpendicular distance from the cylinder's center, pre-rotation and post-rotation. For example, gamma between B and B prime is the same as gamma between C and C prime. When considering torsion in the context of this course, we only consider it for elements as stated earlier. For cylinder elements, as stated earlier, this is because torsion causes different gammas between points at an equal perpendicular distance from the center of other element shapes, such as, for example, a square. This will make the formulas we will derive soon invalid, as they depend on shear strain being constant at the same distance perpendicular from the cross-section center. To create the formula for shear strain, we may consider a small section of the cylinder along its length. The small length being denoted as delta x. Tan gamma is a distance b prime to b divided by distance a to b. This is equal to the radius r multiplied by delta phi over delta x. Delta phi represents the arc length, which is delta phi of a small change in angle between 2 points measured from the cross-section in radians. Gamma is assumed to be small, since delta phi is assumed to be small, which means we can approximate tan gamma as gamma to find the angle. Thus, gamma, or shear strain, is equal to the radius multiplied by delta phi over delta x. Using the radius in this case gives us the maximum arc length from delta phi, so gamma is max when we are using radius as our phi value. To get a general formula for shear stress along a cylinder's cross-section due to torque, we may consider a small circle in the cylinder's cross-section. In this case, ρ represents the perpendicular distance from the center of the cylinder's cross-section to a point on the cylinder's cross-section. The formula for shear strain using ρ is shear strain is equal to ρ multiplied by delta phi over delta x. This function is the same as the function for the max shear strain, except we are using ρ instead of radius, so shear strain is at a perpendicular distance from the center may be expressed as a function of the max shear strain on a cylinder's cross-section. As said previously, the max shear strain occurs at the distance radius. Thus, gamma is equal to ρ divided by the radius multiplied by gamma max. This relationship tells us some important aspects about how shear strain varies along the cylinder's cross-section. First, the shear strain varies linearly going perpendicular from the center of a cylinder to the cylinder's radius. Shear strain is 0 at the center of a cylinder, and shear strain is max at the perimeter, or at the distance farthest from the center. The shear strain is also the shear strain equation is also applicable to a hollow cylinder, that is, a cylinder with a cutout, as seen in the figure. The maximum shear strain occurs at the distance closest to the center of the cross-section, or the minimum, I mean, and the maximum shear strain occurs at the distance farthest to the center of the cross-section, which is the same as before. In this case, is denoted as R2 and R1 on the figure here, with R2 being the max and R1 being the minimum. So does anyone have any questions about how we develop shear strain? Okay, then I'll proceed. Another factor that develops as a result of torque in the cylinder is shear stress, denoted by tau. Shear stress is primarily measured in newtons per millimeter squared, or megapascals. We can find the shear stress from shear strain using Hooke's law. Shear strain is equal to the shear stress over G, where G is the shear modulus in newtons per millimeter squared, or megapascals. From substituting in shear strain, we get shear stress is equal to rho divided by the radius multiplied by G multiplied by gamma max. This is also equivalent to the maximum shear stress multiplied by rho divided by the radius. It is important to note that the shear stress distribution follows the same distribution as shear strain, in that it is at its maximum value farthest from the center and at its minimum closest to the center. Another important aspect about shear stress is that it develops in complementary pairs and flows both perpendicular from the center of the cylinder's cross-section and parallel to the normal direction. This was discussed more in detail during the shear flow lecture. From our observations on shear strain and stress, we may develop a formula for torsion looking at torque. Total torque at a point along the cross-section is equal to the summation of all torque on a cross-sectional area, which is equivalent to the shear stress developed at each area multiplied by distance rho from the center. Substituting in our previous equations, we get that torque is equal to the maximum shear stress divided by the radius multiplied by the integral of rho squared over the cross-sectional area. This formula can be further broken down. The maximum shear stress divided by the radius may be generalized to shear stress over rho. The integral of rho squared over the cross-sectional area is a factor called the polar moment of inertia and is measured in millimeters to the power 4. This simplified formula, rearranging to isolate the shear stress is equal to torque multiplied by rho over the polar moment of inertia. The polar moment of inertia, J, is a section property. It is similar to the second moment of inertia in beams in that a greater area is able to better resist force. This formula for a solid cylinder section for J is given by pi multiplied by the radius to the power 4 divided by 2. For a non-cylinder section, J is given by pi divided by 2 multiplied by the outer radius to the power of 4 subtracted by the inner radius to the power of 4, as seen in the figure here. Does anyone have any questions about how I develop shear stress? Okay, then I will proceed on how to find twist angles in cylinders. So the last topic to consider when looking at torque effects on a cylinder is twist angle, mentioned previously to be phi. From the previous formula, we get delta phi as a function along the beam's length of torque divided by the shear modulus and polar moment of inertia. Across a section with the same properties, phi can be written as simple torque multiplied by length divided by shear modulus and polar moment of inertia. However, across sections with different properties, the rotation angle is the summation of rotation caused by torque at each individual section along the cylinder's length. This will be explored more in depth in our example. So I know that was a quick topic, but does anyone have any questions on how to find the angle, or specifically the formula that we discussed? Okay, then I'll move on. So now we will look at an example of finding twist angles on a cylinder. Consider the following segmented shaft made of cylinders with the denoted properties. The shear modulus of every segment is 11.6 multiplied by 10 to the power 6 per square inch, pounds per square inch. We must determine the maximum shear stress experienced in the shaft and the angle of twist at point C. And I know the units for this are imperial, but you're going to see a lot of that, so you just have to deal with it. So to solve this problem, we must first determine the dimensions of each segment. Then we must find the torque in each segment, followed by a polar moment of inertia in each segment. This will allow us to find the shear stress in each segment. Then we will solve the rotation at the needed segments. In this case, we will need to solve up to point C. The units of torque in the problem are kips multiplied by inches, and length is in inches. A kip is 1,000 pounds, in case you were curious. The length of each segment is simply 25 inches. The radius of each segment is half the diameter of each segment. And the numbers are shown on this slide for each segment. Next, we must solve for the torque in each segment. To solve for the torque in each segment, we may consider the torque profile along the cylinder. So this works similar to bending moment diagrams. Torque generally must be 0 at the free end and must be 0 at the support due to equilibrium. As we see in the torque profile, the torque is 32.5 along segment A to B, 19 along segment B to C, and 9.2 along segment C to D in units kips multiplied by inches. Some general aspects about the profile to note are as follows. If we start from the free end, the torque adds in magnitude in each segment, or if we start from the fixed end, the torque subtracts in magnitude in each segment. The torque should be 0 at both ends to achieve equilibrium. Now we must solve for the polar moment of inertia in each segment. As all segments are solid, this is given simply that the polar moment of inertia is equal to pi multiplied by the radius to the power of 4 divided by 2. The numbers for each segment are on the slide. Note J increases if the segment has a greater radius. Next, we may solve for the shear stress at each segment. We know that shear stress is equal to torque multiplied by rho divided by J. Since we are looking for the maximum shear stress, rho is equal to the radius. The numbers for the maximum shear stress in each segment are on the slide. This max shear stress occurs in segment BC, so that's where we primarily focus our design on, as that's where a failure would likely occur. Now we must solve for the rotation at point C. As established previously, the rotation of a cylinder is given by the summation of all previous rotations along different segments as a result of torque. In our case, the rotation at C is the summation of rotations of segments AB and BC as a result of the torque at those sections. Adding the rotations at those segments using the properties and torque of segments AB and BC, we get that the rotation at point C is equal to 0.153 radians. From this solution, we get some important takeaways regarding how to solve rotation problems. As stated previously, the summation formula for rotation means that the rotation at one point is the summation of the rotation of prior segments. We must consider the rotation of each segment due to torque. In this case, we needed segments A, B, and BC. However, if we wanted to solve for the rotation at D, as you can see, that's at the very end, the pre-end of the shaft, we would have needed the rotations of AB, BC, and DC. Conversely, if we wanted to solve for the rotation at B, we would only have needed AB. To generalize this result, starting from the fixed end of a shaft, the farther a point is along an element's length, the more segment rotations must be added to find the rotation of that point, assuming we have multiple segments making up the shaft. So does anyone have any questions about that example in particular, or how I solved any steps? Okay, then I will proceed. So the last topic that must be examined for torsion is transmission shafts. A cylinder may be used as part of a power transmission device, such as a gear or pulley system, as said earlier. The factors governing how cylinders act as transmission devices are the power transmitted and the speed of their rotation. This relationship is in the form power is equal to torque multiplied by angular velocity. Power P is in Newton meters per section, or watts. Torque is in Newton meters, and angular velocity, omega, is in units radians per second. Fun note about angular velocity: if you call angular velocity W because the omega symbol kind of looks like a W, Professor Schaaf's class, he'll pretend to not know what you're talking about, and he won't answer your question until you refer to it as omega. To further understand transmission shafts, we can look at how to rewrite this relationship in terms of rotations. W, I mean omega, determines the rotation angle traveled for a given change in time. Omega may also be expressed as 2 multiplied by pi multiplied by frequency, where frequency, denoted by f, is the number of revolutions the circle completes per second. We can substitute this relationship into the power formula to solve for torque as a function of power and frequency, as seen on the slide. To help us better understand transmission shafts, we can look at an example involving a system of two pulleys. In the pulley system shown, R2 is the outer diameter and R1 is the inner diameter of each pulley. Pulley A is experiencing a power of 100 watts, which causes it to rotate 200 times per minute. We must find the maximum shear stress experienced by the shafts of the pulleys. The shafts are the white circles, or the white area, in the center of each pulley. To solve this shear stress, we must follow these steps. First, we must solve for angular velocity for the pulley whose rotation per unit time is given, in this case pulley A. Then we must solve for angular velocity of the second pulley, pulley B. After, we can solve for the torque in both pulleys and use this torque to determine the shear stress in the shafts of both pulleys. To solve for the angular velocity in pulley A, we must convert the rotations per minute into rotations per second and use the formula described before to solve for angular velocity. Doing so gives an angular velocity of 20.9 radians per second. Next, we must solve for the angular velocity of the second pulley. As both pulleys are connected to what we assume to be a rigid cable, the pulleys must have the same tangential velocity, denoted by v. V is equal to the radius multiplied by the angular velocity. Since the tangential velocity of both pulleys must be the same, pulley A's radius multiplied by pulley A's angular velocity must equal pulley B's radius multiplied by pulley B's angular velocity. The radius we are using is the outer radius, R2, as seen in our previous figure of the problem. Solving for the angular velocity of pulley B through isolating from the equation gives an angular velocity of 29.9 radians per second. As a general note, a smaller pulley must have a larger angular velocity to compensate for its smaller radius. Next, we can solve for the torque in each pulley. Using the formula torque is equal to power divided by angular velocity, the torque in pulley A is 4.78 Newton meters, and the torque in pulley B is 3.34 Newton meters. Power is the same for both pulleys in a system, as we assume there is no loss due to friction. Also, the larger pulley has a greater torque as a result of its lesser angular velocity. Finally, we can solve for the shear stress in the shafts, denoted by the white area at the centers of the pulleys. Recalling the general formula for shear stress is given by the torque multiplied by rho over J. When solving for the maximum shear stress, rho is equal to the radius. J is equal to pi multiplied by the radius to the power of 4 divided by 2. We use the formula for a solid cylinder in this case for the pull-in moment of inertia, since the shaft does not contain any hollow area on its cross-section. Using this formula and substituting in the corresponding values for the shaft of pulley A and pulley B, we see pulley A's shaft experiences a shear stress of 24,344 pascals. Pulley B's shaft experiences a shear stress of 49,593 pascals. So does anyone have any questions about that problem and how power works? Okay, thank you for listening to my presentation. I hope you learned a little something about torsion, and this is a helpful link that helped me with a lot of my derivations. So thank you for listening.